Today we're taking apart a switching power supply to see how it works. Under the PCB, we have diodes, capacitors, transistors, and resistors. Here's a transformer and an optocoupler which turns on once power is applied. To make it easier to understand, let's rearrange the circuit. Now we can see all components and connections. The red wire is live and the black wire is neutral. First, we have a resistor from the color bands and table. It's 2.6 ohms. This is a gold band, not a yellow one. It's a fusible resistor protecting the circuit from overload damage. Next is a bridge rectifier made of 4 1N4007 diodes and a 450V 2.2 microfarad filter capacitor. This circuit turns AC into DC. This is an oscillator that converts DC back into high-frequency AC at 15 to 50 kHz. Here we can see the component values. This is the S8050 transistor and its pin layout. This is the 13001 transistor and its pin layout. Here's a diode that looks like a Zener, but it's actually a fast-switching diode. The 1N4148 and the 50V 22 microfarad capacitor form the AC to DC converter for the optocoupler's phototransistor. They form this circuit. This transformer has primary, secondary, and auxiliary windings on the core. The secondary lowers the voltage and the auxiliary powers the oscillator. Then we have a Schottky diode, the 1N5819, with a 10V for 70 microfarad capacitor that converts AC to DC and drives the LED indicator. There's also a feedback circuit made of a PC817C optocoupler and a 4.2V Zener diode. This optocoupler transfers signals without direct contact. On the right is the IR LED and on the left is the phototransistor. When the LED turns on, its light activates the phototransistor and switches it on. This 102 nanofarad capacitor is for safety. It's placed between primary and secondary ground to block any. Let's power it on and see what happens. The green line carries positive voltage and the blue line is negative or ground. We can also see the voltages on the graph. We have a 220V 50 to 60 Hz AC input. This bridge rectifier converts AC into pulsating DC. After filtering with the capacitor, it becomes almost pure DC. We can see DC flowing through the circuit. Now this current flows through a 2 mega ohm resistor into T1E's base and starts turning it on. The transistor isn't fully on yet. It's only partially conducting. Because of the partial conduction, a small current in the primary induces a small voltage in the auxiliary winding. That induced voltage charges a capacitor and the capacitor then drives the transistor fully on. Now the transistor is fully on and current flows freely through it. This switches on transistor T2, which diverts T1E's base current and turns T1 off. As T1 switches off, current to T2 is also cut. Then current returns to T1E's base and the cycle repeats. This happens at 15 to 50 kHz, about 1,000 times faster than the rectifier ripple. So the rectifier looks steady and no longer pulses. At the same time, the auxiliary winding powers the diode, charges the capacitor, and feeds the optocoupler. The diode and capacitor convert the auxiliary AC into DC for the optocoupler. The secondary winding also supplies current, which becomes DC through the Schottky diode and filter cap and lights the LED. But what if the voltage goes above 5 volts? That's where the feedback circuit kicks in. When the output reaches 4.2 volts, the Zener conducts and sends current to the optocoupler. It clamps the voltage to 4.2 volts so the optocoupler's LED stays off. The LED needs about 0.8 volts to turn on. When the voltage goes above 5 volts, the optocoupler LED turns on. The light activates the phototransistor inside the optocoupler. This sends current to transistor T2. T2 turns on, pulling down the base of the first transistor and stopping current in the primary. Then the secondary voltage drops below 5 volts, turning off the Zener and the optocoupler, and the circuit repeats normally. You might ask, why not convert AC to DC directly? Because at 50-60 Hz, the transformer and capacitor would be huge and wouldn't fit into a small charger. So chargers convert 50-60 Hz into about 50 kHz, allowing the transformer and capacitor to be much smaller. To change the frequency, we must first convert AC to DC and then convert it back to AC.